Hello everyone, welcome to our presentation on the Adult Income Prediction Project. Our goal is to build a binary classification model using the 1994 census data to predict if an individual earns more than 50,000 a year. Since income data is often imbalanced, relying solely on accuracy can be misleading. So we designed a robust evaluation strategy. We will focus on the F1 score and the ROC AUC to balance precision and recall. We will also plan to use stratified sampling to ensure our validation results are statistically reliable. Let's look at the data structure. We combine the training and test sets for an unified analysis, giving us about 48,000 samples. And we can see most columns are clean, but we did find missing values in work class, occupation, and the native country. This is an important finding because it means we must include an imputation step in our pipeline later. Here is a quick look at our target variable, income. Even from this simple plot, you can see a clear class imbalance. The bar which represents the income is lower than 50,000 is significantly taller than the bar which represent the income is higher than 15,000. This confirms that we are dealing with a skewed dataset. Then we visualize the distribution of numerical features. Two interesting patterns stood out. First, age is right-skewed, meaning that the workforce in this dataset is predominantly younger. Second, we can look at the capital gain and loss. They are extremely spurious. Most values are zero. For linear models, we might need to apply a log transformation to handle the skewness effectives. We also checked for the correlation to avoid redundancy. The heat map highlights that education and education norm are highly correlated, since they represent the exact same information. We will drop the categorical education column to prevent multi-collinearity issue in our model. Here, we performed a deeper statistical analysis of the class imbalance. The data shows a precise ratio of 3.18 to 1. The majority class accounts for 76% of the data. This number justifies our decision to use F1 score, a dummy classifier predicting lower income for everyone would get 76 accuracy but have 0 predictive power, which we want to avoid. Moving on, we broke down the categorical features. We analyzed attribution like work, class, education, and marital status. A key insight here is marital status. Married individuals have higher probability of being high-income earners compared to those who have never married. This suggests marital status is a strong predictor. To confirm these visual findings, we ran statistical t-test. The p-value of for features like age and hours per week are near zero, mathematically confirming that these features significantly differ between income groups. Finally, based on these findings, we designed our data processing pipeline detailed here. First, for missing value, we will input categorical data using the mode or label them as unknown. Second, for encoding, we will apply one-hot encoding to nominal variables to make them machine-readable. Third, scaling. We will use standard scaler for numerical features like age to help the model converge faster. And lastly, we will remove redundant features and duplicate education clump to keep the model efficient. In conclusion, this analysis gives us a deep understanding of our data structure, quality, and key patterns. We have clear roadmap for future engineering and now ready to proceed the modeling phase. Now let's dive into section 3 modeling. After we clean the data, we set up a robust machine learning pipeline. We choose logistic regression as our model because it provides a solid baseline, performance well on high-dimensional spreads data, and offers excellent interpretability. In our pipeline, we applied standard scalar to numerical features like age and capital gain. And we also use one-hot encoder for categorical variables. We wrapped this into a pipeline object to prevent data leakage. First, we trained an untrained baseline model. Let's look at this result. The accuracy is decent at 85%. However, if we look closely at the memory class, the recall is only 0.59. This means our model is missing more than 40% of the high-income individuals. The confusion matrix in step 2 confirms this. The model is biased towards the majority class. It has a high number of false negatives. This tells us that simply maximizing accuracy isn't enough. We need to address the class imbalance. To improve the model, we first look at the regularization. We compiled L1 lasso and L2 ridge and tuned the regularization strength C. Using grid search CV, we found that L1 regularization with C equals 10 yield the best F1 score. L1 is particularly useful here because it induces sparsity, effectively performing feature selection by driving coefficients of irrelative features to zero. However, as seen in step 4, the performance difference between L1 and L2 was marginal. We proceeded with the tuned parameters, but new regularization alone wouldn't solve the recall issue. This brings up to the most critical improvement. To fix the low recall, we induced the parameter class weight balance equals balanced. This forces the model to penalize mistakes on the minority class more heavily. This impact was immediate. Look at the result. The recall for the high-income class just jumped from 0.59 to 0.83. Although precision dropped, our ability to catch high-income earners improved significantly. This model is much more valuable for our predictive task. In step 6, we tried adding polynomial interaction features to capture nonlinear relationships. However, this did not yield a significant performance boost. suggesting that the linear decision boundary is already quite effective. And then we fine-tune the decision threshold. The default threshold is 0.5, but that's really optimal for imbalanced data. By analyzing the precision recall curve, we calculated that the optimal threshold to maximizing the F1 score is approximately 0.633. We will use this threshold for final prediction. Then we generated a learning curve to diagnose the model's bias and variance. This tells us if we are overfitting or underfitting. Here the blue line is the training score and the orange line is the validation score. You can see that as we increase in the training data, and the validation score improves and converges toward the training score. The gap between the two lines is quite small. This is a great sign. It indicates good generalization. Our model is not simply memorizing the training data, but actually learning patterns that apply to the unsafe data. On the advantage of logistic regression is transparency. In step 9, we extracted the feature coefficients to understand what drives income. And we can see the positive drivers, capital gain and being married are the most strongest predictor for high income. And the occupations like pride house serve strongly indicate low income. This finding aligns perfectly with economical intuition. Finally, we evaluated our optimized pipeline on the held-out test set in step 10. We achieved an accuracy of 80% and maintained a strong recall of 0.83. Now let's place our results in context. This dataset was introduced by Kohavi in 1996 as a benchmark for classifiers like Navier-Bayes and decision trees. His original baseline accuracy was around 84.5%. It is important to note that due to the class imbalance we found earlier, a dummy model already achieves 76% accuracy. Our logistic regression achieved about 85% by significantly exceeding the 76% dummy baseline and matching Kohavi's original benchmark. We have confirmed the validity of our modeling approach. After establishing a baseline with logistic regression, we moved to a more complex model, random forest. Because linear models struggle with non-linear relationships, random forest, as an ensemble of decision trees, can naturally compare complex interaction between features like age and education without manual feature engineering. We started with an untuned random forest. The initial accuracy was 85.2% and ROC-AUC was 0.19 and ROC-AUC was 0.9. This is already competitive with our tuned logistic regression, confirming the power of tree-based models. In step 3, we added some custom feature engineering. We created log transformed features for capital gain to handle skewness and grouped real countries into non-US. Then we used random search TV to tune higher parameters like numbers of trees and the max of depths. The best parameters we found were 200 trees with a max of depth of 13. The Chung model achieved an ROC of AUC of 0.917, a solid improvement. One of the best features of random forest is feature importance. In step 4, we visualize which features matter most. As we can see from the bars, the marital status is over-mirroring the most important features. This visualization builds trust in our models. It's making decisions based on logical, financial, and demographical factors. We also performed threshold tuning again. The precision recall curve shows that the optimal threshold for F1 score is 0.61. By moving the threshold from 0.5 to 0.61, we increased our F1 score to 0.7. Now for the final showdown, logistic regression and random forest. And we can see for the accuracy, the random forest wins with 83.4%, with 81%. And the ROCAUC, the random forest leads with 0.92. And for the F1 score, the most importantly, the random forest achieves 0.7, a significantly 3-point lead out logistic regression. This confirms that the non-linear compatibilities of random forest make it the superior choice for the dataset. To wrap up our project, we successfully built a predictive model for the census income data. And for the data, we identified it and handled severe class imbalance. And for the model, we proved that the random forest outperforms linear baselines. And our model can effectively identify high-income individuals with a balanced recall and precision. If we had more time, we would explore gradient boosting methods like XG for potentially even higher accuracy and conduct a fairness analysis to ensure our model doesn't discriminate against specific demographic groups. Thank you for watching.